The detection itself lasted only a fraction of a second, a single anomaly caught by an automated telescope in Haleakala, Hawaii, on the 4th of January, 2026. But the implications of what Pan-S TARRS had just captured stretched far beyond that quiet morning in the Pacific. The object was designated C/2026A1. It was a comet, and it was not on any of the predicted lists. Over the following weeks, as observatories from Chile to the Czech Republic confirmed the orbital calculations, scientists began to understand two things about C/2026A1. First, its nucleus was enormous, estimated at 11 kilometers across, putting it in the same size class as the object that ended the Cretaceous period 66 million years ago. Second, its trajectory was threading a path through the inner solar system that no comet of this size had attempted in recorded human history. Today, we are going to break down exactly what C/2026A1 is, what the electromagnetic threat from a passage of this kind actually looks like, and whether the scenario that power grid engineers have quietly feared for decades could finally be arriving. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally experienced a major power outage that lasted more than a week? An ice storm? A hurricane? A grid failure? Tell me where you were and what those first 3 days felt like. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it. Now, let us get into it. On January 4th, 2026, the Pan-S TARRS-1 telescope at the Haleakala Observatory in Maui, Hawaii completed its routine wide-field survey of the sky. Pan-S TARRS is automated. It does not have a human being watching through an eyepiece. It photographs every accessible patch of sky every night and feeds those images through a detection algorithm looking for anything that moved. Asteroids, comets, near-Earth objects, anything that should not be there. That night, a faint smear of light appeared in a patch of sky near the constellation Sculptor. It was magnitude 21.5, about 400 times too faint to see with the naked eye. The algorithm flagged it. Within the hour, the detection had been logged, time-stamped, and queued for human review. By January 6th, follow-up observations at the Cerro Tololo Inter-American Observatory in Chile confirmed it was real and moving. The object showed a distinctive fuzziness at its edges, not the sharp point source you get from an asteroid or a distant star, but a diffuse glow astronomers call a coma. That fuzziness is the first diagnostic. It tells you volatile gases are outgassing from a nucleus and catching sunlight. By January 9th, 6 separate observatories on 3 continents had independently calculated its preliminary orbit. The object was a long-period comet, inbound from the outer solar system, on a trajectory that had not brought it through the inner solar system in an estimated 3 million years. They called it C/2026A1. Initial orbital calculations put its closest approach to Earth at approximately 14 months from discovery. That number, 14 months, sounds like a comfortable margin. It is not. Orbital mechanics for a long-period comet incoming for the first time are notoriously unstable. As C/2026A1 warms under increasing sunlight, volatile gases, water vapor, carbon monoxide, carbon dioxide, begin venting off the nucleus in asymmetric jets. Those jets act like tiny thrusters. They push. They are called non-gravitational forces, and they can shift the trajectory of an inbound comet by tens of thousands of kilometers from the original prediction. Every week of new observations changes the picture. On January 14th, NASA's Center for Near-Earth Object Studies, CNEOS, updated its trajectory model after incorporating new non-gravitational force measurements. The revised closest approach distance had shrunk, not to a collision, but to something that made a room full of people at the Jet Propulsion Laboratory in Pasadena stop what they were doing and stare at the screen. To put the revised figure in context, the Earth sits inside a zone of space defined by its own magnetic field, the magnetosphere. On a quiet day, the magnetosphere extends approximately 60,000 kilometers toward the Sun and stretches millions of kilometers behind us in the anti-solar direction. When a solar storm hits, the magnetosphere compresses on the sunward side and stretches on the night side, and the interaction generates electrical currents in the upper atmosphere. Those currents are what produce the aurora borealis. They are also what, in extreme cases, induce currents in long electrical cables on the ground, pipelines, power lines, submarine cables, and can physically destroy the large transformers that regulate voltage in high-capacity power transmission grids. The 1989 Quebec geomagnetic storm took down the entire Hydro-Quebec power grid in 90 seconds flat. 6 million people lost power. The outage lasted 9 hours for some and weeks for others. That was a moderate geomagnetic storm, rated G4 on a scale that goes to G5. C/2026A1's revised close approach path does not put the comet on a collision course with Earth. But here is the problem. The comet's tail does not travel with the comet. A comet's tail is actually two tails, a dust tail and a plasma tail. The plasma tail is composed of ionized gases streaming directly away from the sun at speeds of up to 400 kilometers per second. It is not behind the comet in the direction of travel. It points away from the sun, regardless of where the comet is going. And C/2026A1's plasma tail, millions of kilometers long, dense with charged particles at concentrations orders of magnitude higher than the ambient solar wind, is projected to sweep across Earth's orbital path during a 48-hour window. Not the comet itself, the tail. On February 3rd, 2026, the International Astronomical Union issued Minor Planet Electronic Circular 2026 C63. It contained updated orbital elements and a note, a quiet, technical note buried on page 4, that described the projected plasma tail intersection geometry. 3 days later, the European Space Agency's Space Weather Coordination Center in Brussels convened an emergency working group. The agenda was not about the comet. The agenda was about the grid. There was no coordinated press release, no primetime special, no presidential address. The reason for that silence is more complicated than a conspiracy, and considerably more disturbing. The systems designed to communicate electromagnetic risk to the public assume that solar storms are the threat vector. The detection protocols, the warning chains, the public communication frameworks, all of them were built around the sun as the source of geomagnetic events. A comet's plasma tail as the source was not in the template, and what is not in the template tends not to make the news. To understand what a comet's plasma tail can do to a planetary electrical grid, you need to understand the difference between a solar storm and what C/2026A1 represents. In a typical solar storm, the sun ejects a coronal mass ejection, a cloud of magnetized plasma. That cloud travels through interplanetary space at speeds of 400 to 2,000 kilometers per second. When it arrives at Earth, it compresses the magnetosphere, reconnects magnetic field lines, and dumps enormous amounts of energy into the ionosphere and upper atmosphere. The signature is a sharp, rapid change in Earth's magnetic field called a geomagnetic sudden commencement. Ground-level magnetometers spike. Induced currents race through pipelines and power lines. A comet's plasma tail creates a structurally similar event with one critical difference. A solar coronal mass ejection is a bubble. It arrives, it interacts, and it passes. Peak geomagnetic disturbance from a major solar storm typically lasts 6 to 12 hours, with the most intense phase running 20 to 40 minutes. A comet's plasma tail, at C/2026A1's projected parameters, presents 48 continuous hours of dense, ionized, magnetized material sweeping across the magnetosphere. Not a pulse, a sustained interaction. If the induced current conditions mirror even a fraction of the 1859 Carrington event, the largest geomagnetic storm in recorded history, which set telegraph offices on fire across the United States and Europe, the implications for a 21st century electrical grid are difficult to overstate. To put the Carrington event in context, the telegraph system of 1859 was the most advanced long-distance electrical infrastructure on the planet. In September of that year, operators in Boston, Philadelphia, and Washington reported seeing sparks fly from their equipment. Some disconnected their batteries entirely and found the atmospheric current was still strong enough to transmit messages unaided. The Carrington event induced enough ground current to physically burn out the wiring in telegraph stations from New England to New Orleans. That changed fast. Now replace those telegraph cables with the 250,000 miles of high-voltage transmission lines that crisscross the continental United States. Replace the telegraph key with 800 extra high-voltage transformers, each weighing up to 900,000 pounds, each taking 12 to 18 months to manufacture and impossible to ship by truck when roads and logistics infrastructure are themselves dependent on the power those transformers regulate. The Federal Energy Regulatory Commission has warned for years that simultaneous destruction of 9 to 12 of those transformers in the right geographic locations could result in a blackout affecting the continental United States lasting anywhere from months to years. C/2026A1 is not a solar coronal mass ejection. Scientists cannot predict exactly how its plasma tail's magnetic field structure will interact with the magnetosphere. That is the honest answer, and it is also the terrifying one. The exact geometry of a plasma tail interaction of this type has never happened in the era of modern instrumentation, not in the era of high-voltage grids, and not with a nucleus of this size generating this volume of ionized material. The calculations are being done right now. And the range of outcomes in those models spans from a spectacular aurora visible as far south as Texas, to something that looks, in the worst case, considerably more serious than Quebec 1989. Scientists generally do not conclude worst-case scenarios are probable, but they also do not dismiss them. What we are dealing with here is a genuine uncertainty, and genuine uncertainty about a grid-scale electromagnetic event is not a comfortable place to be. What makes C/2026A1 different from a standard solar storm risk is not just the duration of the plasma tail interaction. It is the ionization density. The outgassing rate of an 11-kilometer nucleus at close solar approach produces a plasma environment with ion concentrations that standard space weather models simply were not built to handle. Engineers who design grid protection systems calibrate their surge arresters and protective relays against a known range of geomagnetically induced current values derived from solar storm data. C/2026A1 is outside that dataset. It is outside every dataset. The difference between a blackout that lasts 3 days and one that lasts 3 months is not physics. It is preparation. And that difference, measured in human lives, is enormous. In October 2012, Superstorm Sandy struck the northeastern United States. At its peak, 8.5 million customers across 17 states lost power. For most, the outage lasted 1 to 4 days. For roughly 375,000 households in New Jersey and New York, it stretched past 2 weeks. Researchers who studied those extended outages found something that did not make the evening news. The people who struggled most were not those who had lost the most physically. They were elderly people living alone, people dependent on electrically powered medical devices, dialysis machines, oxygen concentrators, insulin that requires refrigeration, and people in high-rise buildings where water stopped pumping above the 6th floor the moment the building's backup generator ran out of diesel. The average modern apartment building's generator holds enough fuel to run emergency lighting and elevator service for 48 to 72 hours. After that, the water stops. The elevator stops. The elevator-dependent person in a wheelchair on the 14th floor does not get down. That is Sandy. That is 4 days to 2 weeks, with functioning roads, functioning fuel supply chains, functioning hospitals, and a federal disaster response operating within 48 hours of landfall. Now consider a grid event that takes down not one regional grid, but the entire Eastern Interconnect, the system that powers roughly 2/3 of the continental United States, from Florida to Maine to the western edge of the Plains states, for an unknown duration measured not in days, but in months. That is not a hypothetical invented for this video. That is the scenario that a 2008 Congressional EMP Commission report concluded was the realistic outcome of a severe geomagnetic event equivalent to the Carrington event. The report estimated that in the first year of a nationwide, long-duration grid failure, between 2/3 and 90% of the United States population could perish from cascading secondary causes. Not from the electromagnetic event itself, but from the collapse of every system that depends on electricity. Water treatment, food distribution, hospital operations, pharmaceutical supply, and communications. Compare that to Japan. After the 2011 Tohoku earthquake and tsunami, a triple disaster that killed over 15,000 people and triggered 3 reactor meltdowns at Fukushima. Japan's electrical grid was substantially restored to the unaffected population within weeks. Not because the Japanese were luckier, because for 3 decades, Japan had invested in grid hardening, in backup generator standards requiring 72 hours of on-site fuel, in hospital emergency protocols that assumed grid failure as the first scenario rather than the last. The difference between Japan's recovery and what the United States would face in an equivalent scenario is not geography. It is a decision, or rather, the accumulation of decades of decisions not to act. In the United States, the average large transformer has no electromagnetic shielding. The Federal Energy Regulatory Commission has issued guidelines recommending transformer shielding since at least 2012. Compliance remains voluntary. As of this recording, fewer than 4% of America's critical high-voltage transformers have been hardened against a severe geomagnetic event. 4%. These are not just celestial events. They are human decisions, layered over years and decades, that determine whether a force of nature becomes a manageable disruption or a civilizational crisis. The cost of protecting the most critical grid nodes, estimated at between $2 and $4 billion, is trivially small compared to the cost of the alternative. That program has been proposed to Congress 4 times since 2012. It has not passed. What are scientists watching right now? And what would have to happen for the worst case to become the real case? The primary monitoring instrument for C/2026A1's plasma tail density and magnetic structure is the Solar Wind Around Pluto instrument package aboard the New Horizons spacecraft, which scientists repurposed in February 2026 to take magnetic field and plasma density readings as the comet passed through its sensor range. Those readings are being cross-referenced with data from the DSCOVR satellite, the Deep Space Climate Observatory parked at Lagrange Point 1, about 1.5 million kilometers sunward of Earth, which monitors the solar wind in real time and gives grid operators roughly 15 to 60 minutes of advance warning before a geomagnetic event hits. 60 minutes. That is the warning window we are working with for a standard solar storm. Nobody yet knows if the same detection geometry applies to a comet plasma tail interaction. The plasma tail approaches from a different angle than a solar coronal mass ejection. The DSCOVR satellite was positioned to intercept material coming from the direction of the Sun. A comet plasma tail sweeping across Earth's orbital path arrives from a different vector entirely. Whether DSCOVR's sensors will provide the same 15 to 60-minute warning for a tail interaction as they do for a solar storm is an open question that the Space Weather Coordination Center has not yet been able to answer publicly. The second variable scientists are watching is the nucleus itself. C/2026A1's 11-kilometer core is shedding material at a rate that the Atacama Large Millimeter Array measured on March 14, 2026, at approximately 1.4 million kilograms of water ice per second. To put 1.4 million kilograms in context, that is roughly 420 Olympic swimming pools of water evaporating from the surface of the comet every single second. That material does not simply disappear. It feeds the coma, the cloud of gas and dust surrounding the nucleus, which at C/2026A1's current distance from the Sun already extends nearly 200,000 kilometers in diameter. As the comet continues inbound and the solar heating increases, that outgassing rate will rise. Models suggest it could triple or quadruple by closest approach. A larger coma means a denser, more electrically active tail. Keep an eye on the JPL Horizon System Database, too. CNEOS updates orbital elements for C/2026A1 every 72 hours as new ground-based observations come in. Each update revises the closest approach distance. As of this recording, the trajectory has been refined 11 times. The first calculation put closest approach at 0.18 astronomical units, roughly 27 million kilometers. The most recent calculation puts it at 0.031 astronomical units, just over 4.5 million kilometers. That is inside the orbit of the Moon. That is not inside the magnetosphere. But it puts the comet, and its plasma tail, considerably closer than initial projections suggested. The third variable, and the one that is hardest to quantify, is the interplanetary magnetic field. The solar wind carries with it a magnetic field called the Parker spiral, a spiraling structure that rotates with the Sun. When a comet's plasma tail enters this structure, the two magnetic environments interact in ways that are still not fully predictable. Computer models at the European Space Agency's Space Weather Service network are running simulations of the interaction geometry now. Early results, which have not yet been peer-reviewed, suggest that if C/2026A1's tail magnetic polarity is oriented southward relative to Earth's magnetic field, the same orientation that produced the 1989 Quebec storm, the interaction could sustain ground-level induced current events for significantly longer than the 48-hour tail passage window. Significantly longer. The question scientists cannot yet answer is a simple one, and it is the one that matters most. What is the magnetic polarity of C/2026A1's plasma tail? That measurement requires in situ instruments, a spacecraft physically inside the tail. No such mission is currently funded. No such mission could be planned, built, and launched in the time remaining before closest approach. The answer will not be known until it is too late to change anything, and the window to harden the critical transformers, the 12 to 18-month manufacturing lead time for extra high voltage units, has already closed. So let us resolve what we opened with, the comet that no one is talking about. C/2026A1 is real, it is inbound, and it is being tracked by every major space agency on Earth. What it is not, to be precise about the science, is a guaranteed catastrophe. Scientists at CNEOS, at NASA's Planetary Defense Coordination Office, and at the ESA have consistently stated that a direct impact is not predicted. The orbital mechanics do not support it. C/2026A1 will not strike the Earth. That is the honest scientific consensus, and it is true. But here is the part that is not getting the same coverage. A direct impact is not the only scenario that matters. The comet's tail, dense, ionized, magnetically structured, is projected to intersect Earth's orbital path, The exact interaction depends on variables that cannot be measured yet, and the infrastructure that would bear the consequences of a severe geomagnetic event, the high-voltage transformer network that powers modern civilization, has not been hardened. Not meaningfully. Not at the scale the risk warrants. The gap between what scientists know is possible and what governments have actually done about it is the part of this story that should concern you far more than the comet itself. The comet will pass. It always does. What we will be left with, 4.5 million kilometers of closest approach or not, is the same grid, the same untreated vulnerabilities, and the same voluntary compliance framework that produced a situation where 4% hardening feels like progress. Back to the comment I asked you to drop earlier. If you have ever personally been through a power outage that lasted more than a week, tell me what those first 3 days felt like. Not the inconvenience. What actually scared you? I read every one of those comments, and they tell a story that the official reports never quite capture. Let us get to 5,000 likes on this one. It is the only way the algorithm shows this to the people who need to see it. Let us go. See you in the next one.